Hello students, in this part we will see cylindrical polar coordinate system for 3D. In previous part we have seen spherical polar coordinates for 3D. Now we will see cylindrical polar coordinates. So spherical polar was a generalization of polar coordinates that we have seen in 2D. So this cylindrical polar is also a generalization of polar coordinate system that we have seen in 2D. In spherical coordinate system, we draw a sphere whose center is pole or origin and which passes through given point P, or you can say that point P lies on the surface of the sphere. Now here in cylindrical polar coordinate system, we will draw a cylinder about z-axis such that point P lies on the surface of the cylinder. So suppose this is our point P. Let us take this point as a pole or origin or our point of reference, and these are our three coordinates axes which are mutually perpendicular to each other. Now let us draw a cylinder about z-axis which passes through point P. So this is the cylinder. So now this point P lies at some height z on that cylinder. From the height we will calculate above this xy plane. So the point lies at this height z. But you can see at that height, at this height z, there are again infinitely many points which lies on this circle. Here every point which lies on this circle is having height z above xy plane. So now how to identify this unique point? So right now we know that the point lies on the cylinder at height z. Okay, so the second thing is, what is the radius of that cylinder? So for that, let us take projection of this point on xy plane, call that as P dash. So we will get this circle C dash here, which is on xy plane. Now join O and P dash. So this rho is the radius of this circle C dash here. But you can see here this circle C dash is a projection of this circle here. So both the circles are parallel in the sense they lies on the planes which are parallel to each other. So therefore both the circles are having same radius. Okay, so therefore this rho is called as a radius of this cylinder also. For a right circular cylinder, radius of cylinder is equal to radius of any circle on that cylinder. So this rho is a radius of the cylinder. Now the angle between this positive x-axis and this radius vector OP dash is phi. So therefore the coordinates of P are rho, phi and z. So here this rho tells us that the point lies on the cylinder about z-axis whose radius is rho. Z tells us that at height z that point lies height above xy plane, and this phi tells us on which line that point lies, the line whose angle with positive x-axis is phi. So here you can see this line OP dash and RP are parallel lines, therefore their angle with x-axis is equal, and that is phi. So this is how coordinates for cylindrical polar are given. Now we will see relation between Cartesian and cylindrical polar coordinates. So now consider this circle C dash here. So for that circle, now it is a circle in 2-dimension space, so therefore, or 2-dimension plane, and therefore we'll get x is equal to rho cos phi and y is equal to rho sine phi. Now here the radius is now rho and angle we are taking as phi. So this phi will vary over 0 to 2 pi. Now the relation between cylindrical and Cartesian coordinates is, so x is equal to rho cos phi, y is equal to rho sine phi, and the third coordinate is z. So z is equal to z. So this is how we can convert cylindrical, we can get Cartesian coordinates from cylindrical coordinates. And if you know Cartesian coordinates, then by using this relation we can get cylindrical polar coordinates. So rho is equal to under root x square plus y square, which is pretty clear from these two equations. Then phi is equal to tan inverse of y by x. From these two equations, if we divide y by x, we'll get phi is equal to tan inverse of y by x, and z is equal to z. So this is how we can get cylindrical polar coordinates from Cartesian coordinates. So the summary is this: for two-dimensional plane, by using these two equations we can convert polar coordinates to Cartesian coordinates. By using these two equations we can get polar coordinates from Cartesian coordinates. Similarly for 3D, here using these equations we can get Cartesian coordinates from spherical polar coordinates r, theta, phi. Here we can get spherical polar coordinates from Cartesian coordinates, and here we can get cylindrical coordinates from Cartesian coordinates, and in this last we will get cylindrical coordinates from Cartesian coordinates. Okay, I made mistake here. Here we will get Cartesian coordinates from cylindrical coordinates, and this will give us cylindrical coordinates from Cartesian coordinates. Thank you.